Okay, so we still consider it a von Neumann algebra, and psi naught in H bicyclic vector. And we defined what means the algebra of analytic elements in M. Is the set of those elements in M such that the map IT going to sigma t of A has an analytic continuation. And we saw the following thing. We saw that actually this analytic continuation, if I put here sigma minus I alpha of an element A in A, then this is equal to the closure of the operator delta minus alpha restricted to domain of delta minus alpha. Okay. And then we stated a proposition, namely that A is W dense in M, and that A psi naught it's included in M psi naught intersection M prime psi naught intersection all domains of delta to power alpha, alpha belongs to C, and that not only that A psi naught is dense in H, but the closure of the operator delta alpha restricted to A psi naught, if I close it, I get the full operator delta alpha. So in particular, you have S restricted to A psi naught closure is equal to S, and that S star restricted to A psi naught. This has a meaning because A psi naught it's in M prime. And this is, again, the full operator S star. Okay. And what we proved was that sigma alpha bar, well, it's obvious actually, this by analytic continuation, sigma alpha bar of A star, it's equal to sigma alpha of A star, that sigma alpha of AB, it's equal to sigma alpha of A, sigma alpha of B, of course, for A and B belonging to, and you are right, you have also this thing, sigma alpha plus beta of A, it's equal to sigma alpha of sigma beta of A. Again, for an A in A. All this can be obtained by analytic continuation. Now, by the definition, it's clear that A psi naught it's included in M psi naught, and also is included in the intersection of the domains of delta to power alpha, of alpha in C, namely delta to power alpha of A psi naught, it's equal to delta to power alpha A delta to power minus alpha of psi naught, because this is equal to psi naught, and this implies by the formula I wrote upstairs that this is sigma minus I alpha of A applied to psi naught. Another thing is that the algebra A psi naught is included in M prime psi naught. Namely, if you take an analytic element A. Then you get J of A psi naught. It's equal to J of S of A star psi naught, because S of A star psi naught is A double star, so that A of psi naught. It's equal to, now I write what S is J delta power 1/2. This is S, A star psi naught. This is the identity, so that this is further equal to, you can put a delta minus 1/2 in here, so you get that this is sigma minus I over 2 of A star psi naught. And further, this is sigma I over 2 of A everything star of psi naught. So that this belongs to M psi naught. Hence, A psi naught is J of J A psi naught belongs to J of M psi naught, which by the Tomita theorem is M prime psi naught. And we proved also this thing, that A psi naught is included in M prime psi naught. So this thing is proved. Now, in order to settle the density theorems, we have to provide enough many elements in A. And these elements will be of the following form. I denote the form by sigma sub f of x, which is equal to integral, is by definition, integral from minus infinity to infinity of f of t, sigma t of x, dt, with x in M, and good, whatever good will mean, with a good function f. And notice the following thing, that sigma f of x in psi naught, it's equal to integral from minus infinity to plus infinity of f of t. If you apply here psi naught, you get delta t of delta t times x times psi naught dt. Now, if you look at this expression here, this can be, sorry?
Delta to the 8.
Delta to the 80, thank you. This can be denoted as, and it is actually, it is the Fourier transform of the logarithm of delta applied to x psi naught. This is just aside. It's clear that it's such a thing, but it's just aside. We don't need this form. Now, what is more important is to say what a good f means. It means that f has an analytic continuation from the real line. But we don't need any function with a good analytic continuation. We need just some example. And this example will be the function fn of t equal to 1 over root of np e to power minus t square over n. And then for x in M, we will consider xn, it's equal to 1 over root of np, integral from minus infinity to infinity, e to power minus t square over n, sigma t of x dt. And of course, xn psi naught will be 1 over root of np, integral from minus infinity to infinity, e power minus t square over n delta to power it x psi naught dt. Okay, now look at this mapping. The mapping from IR, taking IS into the 1 over root of n pi, integral from minus infinity to infinity, of e to power minus t squared over n, sigma s plus t of x dt. I can change the variable now in order to get here sigma t only, and changing the variable, what is this? Yeah, it is 1 over root of n pi, integral from minus infinity to infinity, of e to power minus t minus s square over n, sigma t of x dt. Or I can write it 1 over root of n pi, integral from minus infinity to infinity, e to power minus t plus I times is. This is minus s there. Okay, sigma t of x dt. And now this map has an obvious analytic continuation. I'm sorry, I forgot to put a square in here, and over n. Yeah. This has an obvious analytic continuation, namely from C containing an alpha, a complex number, is going into sigma minus I alpha of x. This is just a notation for the analytic continuation. It's 1 over n pi, integral from minus infinity to infinity. I just replace there the is by alpha. E to power minus t plus I alpha square over n, sigma t of x dt. And then delta to power alpha of xn psi naught, it's equal sigma minus I alpha of xn psi naught. And it is the same 1 over root of n pi, integral from minus infinity to infinity, of e to power minus t plus I alpha square over n, sigma t of x. Psi naught. Yes, that's correct, but this means delta to power it x psi naught. Okay. Now, we look at these formulas, and we apply on one side the Lebesgue dominated convergence theorem, On the other side, we keep in mind that the mappings t going to sigma t of x are continuous at 0. And then it follows obviously that an, which contains xn, converges either in the W topology or in the SO topology to x in M. And A psi naught, I'm sorry, there is no sub n here. A psi naught contains xn x naught converges to x psi naught belonging to m psi naught. So that we see that A is dense in M, and also that A psi naught is dense in M psi naught, so that it is dense in the Hilbert space, because M psi naught is dense in the Hilbert space. There is one more thing to be proved, namely this one in here.
Your sigma minus I alpha x, how did you get that equal to that?
Where do you mean here?
That equality.
Here.
Sigma minus,
I just copied it from here.
but sigma minus I alpha, I thought was really just.
No, this is, look, this is an extension of the map. IS is going to this, and you see the IS in here. So that instead of the IS, I put a complex number, just a complex number.
Sigma minus
Sorry?
Once it is analytic, there is this description of that. So you're showing that it is analytic.
no, but sigma I alpha already had a different meaning.
Now, I have the IS accounts for an alpha, for a complex number.
Of x as being delta alpha.
No, that was once A is analytic. You have shown it is analytic, then it is equal to.
He's saying that this thing is analytic, right?
Here
There is an
it is showing
extension.
it is analytic.
I just replaced here the IS by an alpha. Okay?
That map has a
You just show it.
It's okay. Fine.
Horizontal
Sorry?
line, straight line integral and upper line integral the same.
Yeah. Well, you can do it also this way, but it's obvious that it is an analytic extension because the variable is here was replaced by an alpha in there. Okay, what we have still to prove, it is this thing here. Namely that because the other things are obvious, for instance, ys restricted to A psi naught, it's as the closure S, because S is J delta to power 1/2. And then if you have this thing for alpha equal 1/2, then of course you have also this thing and the same this here, because S star is J delta minus 1/2. So that the only thing that remains to be proved is this one. So, in order to prove this equality, we take zeta delta alpha zeta, an element in the graph of delta alpha, so that zeta delta alpha zeta is perpendicular on the graph of delta alpha restricted to A psi naught. And what we have to show is that psi is equal, that zeta is equal to 0. That means this equality here. We have to show that conclusion there. Now,
Excuse me, that second line sigma minus I alpha, that will be xn.
the second line, yes. So
Will be xn or x?
here is xn or x. No, it is just any x. It's just what xn? Xn is afterwards.
But next line you wrote minus I alpha x.
I had not an xn at that moment. So thank you. Okay, now what means this? This means the following thing, that zeta A psi naught plus delta alpha zeta delta alpha A psi naught it's equal to 0. And now, look carefully, I will do a mistake first. Namely, I will write this in the following manner. This is, I put delta alpha in here, and what I get, alpha plus alpha bar, it's 2 times the real of alpha. So I get here, it's 1, the identity applied to psi, plus delta to power 2 real of alpha applied to zeta, times a zeta naught is equal to 0. Now, this means it is perpendicular on a zeta naught, but a zeta 0, a zeta naught is dense in the Hilbert space H, as we saw there, so that it follows that this guy here is equal to 0. And because this is an injective positive operator, it follows that zeta is equal to 0. But I said I did a mistake. The mistake is I have not the right to write delta to power 2 real of alpha of zeta, because I know that zeta belongs just to the domain of delta to power alpha, right? So not to the domain of delta to power 2 of real of alpha. Then, in order to do it correctly, I try it in the following manner. I put the delta alpha in this part, and what I get here, okay, I get zeta times 1 plus delta to power 2 of real part of alpha times a psi naught, it's equal to 0. Now, this operator is an injective positive operator, so it has a dense range, but a dense range on its whole domain. And here I have only psi naught. In order to conclude, I would need to know that such an operator is a bounded operator. It is not a bounded operator. And then the reparation to this situation is...
You need this A psi naught is a code for that operator, right?
I have to show that it is a core for that operator. So that I have to make this proof rigorous. And in order to make it rigorous, we replace a psi naught, we replace it from the beginning by exponential of minus delta, exponential of minus delta to power minus 1, a psi naught. This is still an element in the Tomita algebra. But now, what I get here instead of this, I get this operator times exponential of minus delta times exponential of minus delta to power minus 1. So that now this operator is a bounded operator. And then it follows that indeed the range here is dense in H, so that zeta is perpendicular on every element in H, so zeta is equal to 0. I did it so, and I didn't do it from the beginning, just in order, because it would sound very artificial to start with such a thing. But now we see why we have to replace a psi naught by this thing. Okay, so this proves the fact that indeed delta to power alpha, any alpha, restricted to a psi naught is equal to the whole a psi naught. Okay. So the statement concerning the Tomita algebra was completely proved, and what is very good with this Tomita algebra that it is big at the level of the von Neumann algebra M, because it's V dense in the von Neumann algebra, and it's big also at the level of the Hilbert space, because not only AXI naught is dense in the Hilbert space, but it is a core for all the operators delta alpha. Okay. Now, consider the following thing. Consider the set of all x in M, which are left fixed by the modular automorphism. Sigma t of x is equal x for any t real. If I denote phi is equal the state, the vector state omega xi 0, then it's better to put here sigma t associated to phi. And this will be called the centralizer of phi. So either we denote it by C or we put M phi somewhere. Okay, it's clear that since the modular automorphisms act identically on the center, it follows that Z is included in C, which is included in int M. But on the other hand, this is a constant map. IT going in this thing is a constant map. It's IT going to X. So that such a map has obviously an analytic continuation, namely itself, the constant map. Accordingly, this centralizer is contained in the algebra of analytic elements. Okay. So that what we have that if A belongs to C, then delta to power IT, A delta to power minus IT is equal to A. This sigma t of A is equal to A. But this means delta to power IT A is equal A delta power IT. That means that A commutes with delta. There are several definitions for the commutation of a bounded operator with an unbounded positive operator. Among them is this, the commutation with a unitary group associated to the operator. So indeed, the delta commutes with A. And now it's the following thing. What means phi to be a trace? Phi to be a trace would be phi of xa is equal phi of ax for every ax belonging to M. That means that phi is a trace. If phi is not a trace, then we would expect that the modular automorphism group helps us to express the change in this equality. What happens with this equality? And this is indeed so. Maybe I will put here, I will announce from beginning the results, is the following. For X in M, and for A, an analytic element, we have the following. Phi of xa it's equal phi of sigma sub I of A times X. This is the result, and I announced another result also, which I will obtain first, namely that X A psi naught is equal to J sigma minus 1/2 of A star, J x psi naught. Well, this is not artificial.
Is that minus I by 2 or minus half?
Minus 1 I over 2. Minus I over 2. So what we want to do is to change xa into ax, or just to change the order, so that what I am doing here is perfectly justified. Xa psi naught is equal to, this is S of A star x star psi naught. Because the adjoint of A star x star is xa. And this is further as A star S of x psi naught. Furthermore, I can write this in the following manner: j delta to power 1/2 A star, and then S, I put it j delta 1/2, but it is equal also with delta minus 1/2 j x psi naught, which is further equal to j. I look at this thing here, and I recognize here sigma minus I over 2 of A star j x psi naught. Well, this is exactly what I announced here. Fine. It remains written there. And now I attack, say, the equality there. So I put phi of xa is equal to xa psi naught, because phi was the vector functional defined by psi naught. It's equal to j, I apply that formula there, j sigma I over 2 of A star. It seems I changed something, namely this. I changed it with what I wrote there, but this is justified by one of the formulas I wrote before. That sigma alpha of x, everything star, is equal to sigma alpha conjugate of A star inside. So that is this thing, j x psi naught, x psi naught, psi naught. Furthermore, this is equal to, I put a j in here, but I have to change the order because j is conjugate linear. So this is equal to j psi naught times sigma I over 2 of A star I'm sorry, no. This is, no, is minus. I wanted to change, and so I have to put the star outside. That's okay. Yeah. So that this is the star outside, j x psi naught. It's equal further with sigma I over 2 of A psi naught of A psi naught j psi naught. Let me understand what I did here. Yeah. Of course, is this thing. Because j of psi naught is equal to psi naught, and this guy went in the other side because it was an adjoint. And then with this thing I go to x psi naught j of sigma I over 2 of A psi naught. What I did, I put the J as a J star, which is equal to J in here. But I changed the order because of the complex conjugate linearness of J.
Somewhere there, right?
Sorry?
Sigma I by 2 ax,
Here is sigma I over 2 of A applied. Now look from here. This is applied in here, right?
Right.
So that it's correct what is there.
Jx sin naught.
J, thank you very much. Jx psi naught. Okay. Now, what I did, I put the J in the other side, but I changed also the roles. So this is further equal to x psi naught, and I write here what is this. This is delta 1/2 S. This is J, is the J in here, because S is J delta 1/2. If you put a J before, you get a J square, which is the identity of sigma I over 2 of A psi naught, which is equal to further x psi naught times sigma minus I over 2 of sigma, no, I'm sorry. Right. Is delta power 1/2 sigma minus I over 2 of A star. I change this with this thing again. Okay, then delta power minus 1/2 of psi naught. I just wrote instead of psi naught, I wrote delta power 1 minus 1/2 because it's the same thing, right? Okay. So I put artificially this here, but because I want to read it in the following manner, this is x psi naught times sigma minus I over 2 times sigma minus I over 2. You see? This is sigma, the first sigma minus I over 2. And inside, you have already a sigma minus I over 2. So I put it twice of A star psi naught, which is equal to further, is equal to x psi naught times sigma minus I of A star psi naught. I just added these two guys, and this is equal to x psi naught sigma I of A star psi naught, which is indeed sigma I of A x psi naught psi naught psi naught, which is equal to phi of sigma I of A x. So indeed, I got the announced equality. Okay. Now this equality is very important. It is very important. On one side, for our soul, because we see how changes the trace equality. But on the other hand, it is very important because this equality here characterizes the modular automorphism group. Because now the construction of the modular automorphism group was laborious. But now we will have a condition which says if a group of automorphisms invariates the state phi and satisfies such an equality, then that group of automorphisms is the modular automorphism group of the state phi.
Means that this thing is like KMS condition.
Exactly. So that this will be the KMS condition. But we will write this KMS condition without using such an extension, an analytical extension. We will write it without using analytical extensions of sigma. So we will have just to translate it. Now, in particular, if you have A belongs to C, then these equalities become phi of xa is equal phi of ax for every x.
Not complex numbers, you mean the central.
I'm sorry, yeah, the M phi, the centralizer C, yeah, thanks. We have this equality. So if you take an element in the centralizer, you have the trace equality. And on the other hand, this other equality writes xa psi naught is j a star j x psi naught. Which now imagine where if j would have been equal to s, this would be, if I replace this j by s, this is obvious for every element.
Yeah, I have a silly note. That last equation,
You mean this one? Yeah?
on the right side, the first bracket J is.
No, what I just wrote this equation.
That, the right side of that equation,
Yes?
I'm observing that x commutes with the first part, j something j, which comes from m.
I don't see why it commutes. The commutation is this one. xi, if you want to reverse, you have to put this thing inside of A.
Jmj is contained in m prime, right?
Jmj is contained in M prime. Okay.
Yeah, but is sigma minus I over 2s are not in m?
Oh, you can put it in there. Of course, you can put it.
If you
Yeah, it's actually.
over there, then it says that x kills a minus that vector of psi naught for all x in m.
That's true for all x in M, but also for A analytic.
But A is in analytic, A is not for all limits.
No, I understand, but I'm trying to say that seems to say that for all analytic A is I naught, then that same equation, I'm just saying whether for x equal to.
Okay, here the fact that A is in the centralizer means that this is equal to A star.
Yeah, but you're saying that it is separating solutions.
Okay.
No. M, all of m kills something when the thing at bottom is 0. No, but anyway, it's a duality for x equal to 1. It says what I was trying to say. If that equation with x equals 1 is equivalent to this. It's not the same. Because they have different techniques.
Okay. So what I'm doing now, I want to explicitate that KMS condition I wrote there without using analytical extensions. And this happens in the following manner. First of all, I will put 1. Phi sigma t is sigma t invariant for every t. Sigma t phi. Well, now, well, this is obvious. We want to rewrite that equation in there, the first equation I wrote, without using any analytical extension. So let's write this equality phi of x. I write it a. It's equal to phi of sigma I of a x. But I will put, instead of a, I will put another analytic element. I will put the analytic element sigma minus I alpha of a. And then what I have here is phi of x sigma minus I alpha of a. It's equal to phi of sigma I over 1 minus alpha of a x. You see, you have an I here times this gives you exactly this thing. And now I write this equality. This means x sigma minus I alpha of a times psi naught, scalar product psi naught. It's equal to sigma I times 1 minus alpha of a x psi naught times x psi naught. Or this is equal to x. This is delta alpha a delta minus alpha of psi naught times psi naught. And here, what I get the same way, delta power 1 minus alpha, alpha minus 1, I'm sorry, alpha minus 1, a delta power 1 minus alpha, x psi naught, psi naught. Or this one disappears because delta psi 0 is psi 0. And also this one disappears because it goes in the other side and it lives in peace.
How do you write the third line, in the third line of the code? And,
well, I don't understand what is the problem because this sigma minus alpha is delta alpha. Oh, okay. Here. Here.
that to the
Sigma A,
I replace it in here. I replaced A by sigma minus I alpha of A. Right? It's okay. Good. So that what I get this equality, x delta alpha of psi naught, it's equal to this. Okay. And I write it now in the following manner, x delta power alpha of a psi naught times psi naught, it's equal to x psi naught times delta, the conjugate of this, it means 1 minus alpha bar. And I put also the a star in the other side, it is a star psi naught. So this is the equality I want to use. Now, look at this equality. And the left hand side of it has a meaning even if A in M is arbitrary, so that not necessarily an analytic element, and 0 less than real of alpha less than 1/2. This is because A psi naught belongs to M psi naught, which is in the domain of S, and the domain of S is the domain of delta power 1/2. So if delta power 1/2 has a meaning on it, it means that delta alpha for every real of alpha less than 1/2 has a meaning. Because I gave to you the description of what means delta alpha. You have an analytic extension up to the real of alpha. If you have an analytic extension up to here, then you have an analytic extension also up to here. So that this has a meaning of this. Now, right-hand side. Has a meaning even if A in M is arbitrary, and real of 1 minus alpha bar, it's less than 1/2 for the same reason. But what means this? This means 1/2 less than the real of alpha less than 1. This is because, again, A star psi naught belongs to M psi 0, and you have here A star psi 0. Okay, so due to this equality, we can define a function f defined on alpha in C such that the real of alpha is between 0 and 1, values in C, in the following manner. F of alpha, it's equal to the first thing, x delta power alpha A psi naught times psi naught if 0 less than real of alpha less than 1/2, and as the other thing, x psi naught times delta power 1 minus alpha bar A star psi naught if 1/2 less than real of alpha less than 1. Now, this function, you have here 0, here you have 1, and here you have 1/2. This function is obviously analytic in here, is obviously analytic in here, and it's continuous on the whole thing because of that equality there. So that this is a removable singularity, so that the function so defined is a function which is continuous and bounded on the whole strip with the ends, and which is analytic everywhere. Is analytic also on the 1/2 line. So that this is an analytic function. And what we have f of it is equal to x delta power it a psi naught. Psi naught is equal to, I write this, this is phi of x, here I think so, delta power it, a delta power minus it of psi naught, so that this is sigma minus, sigma minus t. But I will put, instead of minus t, a sigma t. You know, it's sigma t because here is delta power it, a delta power minus it of psi naught. So this is sigma t of a psi naught. And I write this sigma t as sigma t of a is okay. All right. So this is f of it. And f of 1 plus it, f of 1 plus it, it's equal to the same computation, a similar computation. It's phi of sigma t of a x. Okay. This is, say, analytic. In order not to write bounded and continuous on the closed strip and analytic in the interior, I just write analytic in here. So that what we got that for every x in M and for every a in M, we have a function which is analytic in this strip and which has these values on the boundary. Now, you see what a nice appearance is here, because it is like a trace thing, but not, it's one is here and the other one is at 1. It's in here, this. This is the KMS condition. And I will say this is 2.
Actually needed the equation only for real alpha.
Sorry?
You actually needed the equation
Yeah, I needed to have this equality.
only for real alpha equal to half.
Sorry?
You only needed this for real alpha equal to half.
Exactly. Yes, because I got a function on here. This was 0, this was 1, was analytic in here, and continuous because of this everywhere, right?
Yeah, okay, but I'm saying
So-
initially you had something more,
Yeah,
but you're only using it on the line.
just on the middle line. Okay. So this is, say, 2 and 1. And these two conditions, 1 and 2, characterize the modular automorphism group. That means if you have a one-parameter automorphism group of M, which leaves invariant the positive form phi, and which satisfies that condition there, namely for every x and a in M, you have an analytic function such that, right? Then necessarily sigma t is equal to the modular automorphism group. And I hope I have half an hour more, right? I hope I can prove it. But in order to prove it, I want to avoid repetitions so that, let me recall you what is the Fragment-Lindelöf principle. You have such a thing between 0 and 1, say. You have a strip like this. And you have an analytic function in here, which is analytic. analytic and bounded. Then the function is bounded by the values on these two lines. This is a fragment one of the forms of the fragment Lindelöf principle. So that if you have an analytic and bounded function, which is in here, then if it is bounded by 3 on these lines, then it's bounded by 3 everywhere. Right. Sorry?
Yeah, this is it is unbounded.
Well, if you want, instead of being bounded, you can put a different growth condition. But we will need it only in this manner. And now, assume you have a sequence of analytic functions, Fn, bounded. And you know that this sequence is a Cauchy sequence if you look it on here and here. Then it follows that it is a Cauchy sequence everywhere. So it will define a function everywhere in here. So this is the device I will repeatedly use in what follows. Okay. Make sure I have the cheat sheet with me. Fine. Now, the first condition, this condition, means that the map M psi naught, taking an x psi naught, going to sigma t of x psi naught, belonging to M psi naught again, this map defines these maps. Define an SO continuous unitary group. So these maps UT can be extended to unitary operators because of this invariance in here. Okay, good. So that what we have ut of x psi naught. It's equal sigma t of x psi naught. Okay. Now, if you take an A in M, you have the following thing. Ut s of A psi naught, it's equal ut A star psi naught. It's equal sigma t. Well, ut of psi naught, it is ut star of psi naught, it is psi naught, as you see from the definition. So here you get indeed sigma t of A star of psi naught, because you can put here an ut star without changing anything. This is equal sigma t of A star psi naught, and this is equal to S of sigma t of A psi naught, which is equal to S of ut of A psi naught. So that it follows that the unbounded operator S commutes with ut. If it commutes with ut, it follows that also S star S commutes with ut. That means the delta operator commutes with ut. Right. Of course, what we checked there was the commutation on a core of X, but we extended it to the closure. Okay. Now, we use the KMS condition. It is still written there. Okay, it's still written. We use the KMS condition. We see that for every A and X in M, there is a function f defined on, well, I will put just this, 0 real of alpha less than 1. Bound are continuous, bounded on the whole thing, analytically in the interior, with values in C, such that we have f of it is equal to phi of x star sigma t of A is sigma t of A psi naught x psi naught. And this means ut of A psi naught times x psi naught. On the other hand, we get in the same manner f of 1 plus it is equal to a computation like this, gives to you the following thing: s of x psi naught times ut s a psi naught. So what we have is the following thing. We have f to power it. It's equal to ut zeta psi, and f of 1 plus it it's equal to s zeta times ut of f zeta. For zeta is equal a psi naught belonging to m psi naught, and for xi it's equal x psi naught, it's belonging to m psi naught. Now here we have involved here the S operator. The closure of the S operator restricted to m psi naught is the whole operator S, so that I can extend this relation here for every zeta in the domain of S and xi in the domain of S. That means for every zeta in the domain of S and for every psi in the domain of S, there is a function f such that, and this function is obtained exactly as I said before, because you get an approximation of, say, psi. You get an approximation of psi with psi adds in m psi 0 such that with x and psi 0, and such that s psi n tends to psi and s psi n tends to s psi. Of course, psi n are in m psi 0. And because of these convergences, and you look what is involved in here, you see that the corresponding sequences will converge on the whole and will define a new analytic function, namely f. Okay, now let's write it in the following manner now. It is f of it it's equal ut zeta times xi, and f of 1 plus it it's equal ut delta zeta psi, and this is valid for zeta in the domain of delta and xi in the domain of S. The only problem we had we had, you see here, I put S in the other side. I reverse the order. I put S in the other side. S star comes here. S star commutes with U. So I get ut S star S zeta. That means delta zeta. This is correct only if zeta belongs to the domain of delta and psi belongs to the domain of psi. Okay. Now, we see that the domain of S is dense in H. And with the same trick as the one announced there, I can extend this equality with another function, of course, for psi in H, because d of S, it's okay. Now, U was a unitary, a group of SO continuous group of unitary operators. So ut is a to power it with the analytic generator of a, right? Good. And what do you want? Sorry?
How can we extend the second one? Can you tell me?
I said
If 1 plus it ut delta.
I said it at the beginning. I look at what happens on the borders, and there you get a Cauchy sequence of functions. So it is a Cauchy sequence of functions on the whole thing by the Fragment-Lindelöf principle, right? And so you get a Cauchy sequence, so you get a new function. I applied this twice.
So, but what is the analog of the right side of the equation?
Sorry?
So if you're given Chandler vector xi and e, what is that?
Now, what I say is the following thing. I have this equality here.
Fine. No, I didn't see the domain delta. I thought you were taking both the days.
Yeah, of course. So, this equality, which was first valid for these things, is valid for such a thing and C in the domain of S if zeta is in the domain of delta. Okay, now, what I want to show, and this will end the story, is that delta is included in A. So I take an element in the domain of delta, and I want to show it is in the domain of A, and the values of delta and A are equal. Okay. Well, from what we saw there, mainly this thing for psi is in H, what we see that for zeta in the domain of delta, the mapping IR contains IT, goes to UT of zeta, has an analytic continuation on the strip real of alpha on this thing, on this strip. And this means that zeta is in the domain of A. And the value in 1 is A of zeta. A of zeta is the value in 1, but the value in 1 is delta zeta. So that this is a very easy thing just because of this analytic continuation in here. And that means that indeed delta is included in A. That means A star is included in delta star, but they are self-adjoint, so I have also the other inclusion. And so indeed, I have that A is equal to delta. Consequently, if I put sigma t of x, sigma t is the abstractly given group of automorphisms. I want to show it is sigma t of phi. And sigma t of x psi naught, it's equal to ut x psi naught. It's equal to a power it x psi naught. It's equal to delta power it x psi naught. It's the end. Delta power it x delta power minus it psi naught. It's equal sigma t phi of x psi naught. This is equal to this because the vector psi naught is separating. It was bicyclic. Well, the same result, exactly the same result, is true when instead of a normal positive form, you take a normal semi-finite fightful weight, except that then the conditions in here will be applied to what is this? My cheat sheet is not here. No, it should be, yeah. Here x and a should be in n phi intersection with n phi star. That means they should be in the algebra. Notice that in case of a positive form, a sub phi is exactly m psi 0. So that this is exactly the statement in the case of weight. And I think that giving the proof for a normal functional was enough and better because we avoided artificial complications. So that's it.
Are you saying the weight it's like?
So, no, I have still 10 minutes. Okay.
For weight, still you need proof.
Sorry? It's the same proof like here. But I will not enter the details of that proof in order to avoid more or less artificial complications. So for that reason, I consider it just finite weights. Okay. Now, because I have still 10 minutes, let's take advantage of them. We considered the centralizer C, which is m phi, which means all the elements x, a in M, such that sigma t phi of A is equal to A for every t a real number. Okay. And what I want to show that this is equal to the A in M, such that phi of xa is equal phi of ax for every x. This, if the modular automorphism group is in some sense a little trivial, then you get immediately the trace equality. Okay, well, let me not go into the details. You will have them written. The point is the following. You will find that the function there, which is defined in here, is bounded on this strip. So it will be bounded everywhere. An analytic function which is bounded everywhere by Liouville, it's a constant function and so on. So that this is a characterization of the centralizer, and because I need to drink some water, I stop here.